Okay, let's unpack this. We've got a paper here that feels like a massive shift in how we think about autonomous agents.
Yeah, this one's a big deal. The title is Lumen, the first AI agent to complete hours-long missions in real time within expansive 3D open worlds.
And we're not talking about, the old playgrounds like Atari or even the complex strategy of StarCraft 2.
No, not at all. This is Lumen, a generalist agent autonomously completing these huge multi-stage missions in a commercial open-world game, Genshin Impact, for almost 5 hours straight.
That's the milestone. It's pairing that kind of scale with just unprecedented efficiency.
Right. Lumen is a 7 billion parameter vision language model, a VLM, and it's built on Qwen 2 VL7B base.
But the real magic isn't just the size, is it? It's this architectural choice they made.
Exactly. They call it hybrid thinking. The agent basically decides on the fly if it needs to do complex interpretive reasoning or if it can just, act. That's the key to making it playable in real time.
And the data behind it is just staggering. We're talking a multi-stage training process that's anchored by, 1,731 hours of high-quality human gameplay?
Yep. Pure, action-centric pre-training that taught it how to just be in that world.
But the thing that makes it all work, the real engineering success, was cracking the latency problem.
For sure. Open-world games need a super strict interactive control loop, usually around 5 hertz.
So the whole see, think, do has to happen in under 200 milliseconds.
And they got there. A 25.3 times speed up, which brought the latency for that critical first action chunk down to about 110 milliseconds.
And finally, the part that makes it a true generalist agent story, it generalizes.
It really does. It doesn't just master new parts of Genshin Impact. It successfully transfers its skills, zero shot, to totally new games.
Like the action RPG Wuthering Waves, and even, which I found amazing, the turn-based strategy game Honkai. Star Rail.
It's proof that this foundational model approach can create a robust decision-making control system that operates under the insane constraints of a live commercial product.
Okay, so let's dig into that environment. Why Genshin Impact? What makes it such a demanding test bed compared to, say, Go or other sims we've seen agents conquer?
Well, open worlds are just a fundamentally different beast. There's no single clean objective to optimize for.
Right.
Genshin is this massive third-person action RPG. It demands hundreds of hours of really complex, long-horizon progression. You're dealing with sophisticated 3D navigation, climbing, gliding, diving in this huge, unpredictable world.
And it's so messy. It's not just about movement.
Exactly. It's completely multimodal. You've got real-time combat, you have branching NPC dialogue, you have complex inventory and UI management, and then you have puzzles that need real spatial cognition.
It just ticks every single box for complexity. The paper actually lays out these 6 core challenges they had to solve.
They do, and it's a great summary of the problem.
Let's run through them, because I think it really defines the scope here.
Okay, so first, scalable environments. You need rich, diverse dynamics. Second, multimodal perception, which is crucial. Fusing that 3D visual world with all the 2D stuff like the mini-map and UI text.
Then you've got high-level planning, has to be long horizon, has to be adaptive.
Followed by low-level control, which is translating those big ideas into actual precise keyboard and mouse actions. Fifth is memory, keeping track of what's happened.
And the last one, the one that makes this whole thing possible in a real game, real-time inference. Thinking, but thinking fast.
Which brings us right back to how they solved that thinking problem. It's all built on that 7 billion parameter VLM.
So why 7 billion? That seems huge. Couldn't they have gotten away with a smaller model if they were just focused on game actions?
That's a great question, and they actually have this fantastic insight from a scaling study they did.
Okay.
They found that a smaller 2 billion parameter model actually started to degrade. It started overfitting after they fed it about 1,200 hours of the gameplay data.
So the bigger 7B model was necessary just to absorb all that data without breaking.
Exactly. To maintain performance stability as the data grew, you needed that larger capacity. It really validates the whole foundation model approach for this kind of complex behavior.
So with the capacity sorted, they focus on efficiency with this hybrid thinking idea. We've seen agents like React that, reason every single step.
Which is computationally impossible for a game running at 5 hertz.
Right. And we've seen hierarchical models, which can be unstable. So what's different about Lumine's approach?
It's trained end-to-end to be flexible about its cognitive load. I kind of think of it like a professional athlete. They're only doing that explicit inner monologue, the planning and reflecting at critical moments.
I see.
It uses a special token, thoughts start, but only when it really needs to. The rest of the time, it's just in a flow state, outputting actions directly with action start.
So that reasoning just naturally emerges when a plan fails or a task is done or a new goal pops up. It's smart reflection, not constant navel-gazing.
You got it. And the action space is brilliant. They didn't use complex code or separate action heads. They just unified every possible keyboard and mouse operation into a single, concise language space. The model just generates it like text.
Which brings us to the training, a really meticulous 3-stage pipeline.
Yeah, was free training. They took those 1,731 hours of human data, focusing on the main story and high exploration in the starting area.
Okay.
But, and this is key, they mixed it with about 20% general multimodal web data.
To stop it from forgetting how to be a general VLM.
Exactly. That created what they call Lumen base.
Then stage 2, instruction following, fine-tuning that base model to actually follow goals.
And finally, stage 3, reasoning. They refined it again to make sure it only generated that inner monologue, that thought token at the right moments. And that gives you the final agent, Lumen thinking.
Okay, now for the core engineering question. How did they cheat the clock? Hitting that 5 hertz, that 200 millisecond deadline, is brutal for a model that normally takes seconds to respond.
It was a massive systems problem.
Yeah.
Their initial latency was over 3 seconds.
Wow.
Yeah. The 25.3x speedup came from a few really clever tricks, but the most important one was streaming output.
Okay. Explain what that is and why it's so critical here.
So instead of waiting for the model to generate a full sequence of actions like move forward, look up, jump, which might take, say, 300 milliseconds, they broke the output into tiny chunks, 6 of them, each taking about 33 milliseconds. The moment a chunk is finished, signaled by a semicolon, the game just executes it immediately.
So they're basically running inference and execution in parallel. They don't wait for the whole paragraph. They act on the first word as it's being written. But doesn't that risk, overshooting or miscoordinating things?
Oh, it absolutely introduces risk, especially for fine-grained control. But it buys them crucial time. And to manage the model's context during all this, they got smart with KV cache management. They used the streaming LLM technique. For those not deep in LLM architecture, it basically means they anchor the system prompt as an attention sink, which lets them reuse the historical memory cache efficiently when their context window fills up.
That's a very clever way to handle memory under pressure. And they did more on the optimization side too, right? With decoding?
Yeah. They implemented a draft modelless speculative decoding. They basically took advantage of the fact that their action space is really structured. It has fixed things like spaces and semicolons to predict the next token super fast, cutting down the number of decoding steps.
And we should probably mention this wasn't just software. This was serious hardware work, too. Tensor parallelism across 4 H20 GPUs, W8A8 quantization with smooth quant. This is top-tier ML engineering.
It is. But even with all of that, they still hit an unavoidable wall, which they're very upfront about in the paper, asynchronous input.
Meaning the agent is always seeing the world slightly in the past?
Exactly. It's perceiving visual inputs that are about 200 milliseconds old. And that delay can really mess with low-level control, cause things like mouse movement overshoot.
Which is why the memory component, the history, became so important. How did that help compensate for the lag?
It worked incredibly well. They found that keeping about 10 historical frames in the context gave them peak performance. And those history-aware models were way less affected by that 200 millisecond lag when they were doing real-time stuff like navigating menus or moving around.
The memory gives it stability.
Yeah, against that temporal lag.
And you see that stability in the results. Lumen finished the first 2 acts of the main story in 4.7 hours. Not as fast as an expert human at 3.6 hours, but that's remarkably steady progress for an AI.
And you see real generalization within Genshin. It could recognize new versions of old puzzles, like it saw a floating stone platform in a new dungeon and immediately related it to a similar puzzle it had solved hours earlier.
That's real pattern matching, not just rote memorization. But the errors are still really telling. Even the best model, the history model, had an 8.8% failure rate in its reasoning. What were the biggest mistakes it kept making?
The 2 big ones were perceptual misrepresentation, which is kind of the AI equivalent of just tripping over nothing. It would hallucinate objects or misread its own status bars.
Okay.
And the other one was premature completion, where the model would just decide a goal was finished when it wasn't, and then start planning for the next thing based on that faulty assumption.
So even with a 7B model and all this history, perception is still the hardest part of the problem?
It seems to be.
Let's talk about the cross-game generalization, because this feels like the really exciting part.
Absolutely. The zero-shot transfer was pretty remarkable. In Wuthering Waves, which is another action RPG, pretty similar to Genshin,
Right.
Lumine was almost at human-level efficiency. It did the starter missions in 107 minutes, and the human average was 101. It just seamlessly transferred its 3D movement and UI skills.
But then they threw out a real curveball. Honkai, Star Rail, a turn-based strategy game. Totally different mechanics, and you can't even jump.
The domain gap was huge. And yeah, it was way less efficient. It took 7 hours versus the human 4.7.
But the fact that it could do anything at all is kind of amazing.
It is. It showed reasonable 3D navigation and GUI manipulation, even though it struggled in combat. Its learned at action space caused problems. It kept trying to jump over gaps that just aren't a mechanic in that game.
But even when it was stuck, it was still trying to solve the problem. I loved the part where it was failing a boss fight over and over.
And it adapted by going into the game's menu and lowering the difficulty setting to finally win.
That is a VLM acting as a flexible control system, not just a game-playing bot.
For sure. It proves the foundation is there for action across different domains. But there are still clear gaps to reach, expert human performance.
What were the main bottlenecks they saw in its actual gameplay?
It was mostly stuff that points right back to the training data for the reasoning stage. Yeah. Well, it almost never used fast travel. It would just walk these incredibly long distances glued to the golden quest marker on screen. It also had a pretty limited understanding of the minimap, and crucially, it never proactively healed itself at statues or by eating food.
Because those just weren't patterns in its initial reasoning training set?
Exactly. So those are solvable problems, right? You just need better, more diverse data.
So what's the path forward? What's the next big research goal?
Scaling is still number one. More training data across more games, more regions, just to boost robustness. But the biggest technical hurdle left is long-term memory.
That 20-frame sliding window isn't going to cut it for a 100-hour game.
Not even close. It's totally inadequate for missions that span thousands of turns. They need much more sophisticated memory systems.
And presumably moving beyond just offline data.
That's the holy grail. To really surpass human performance, you have to integrate online reinforcement learning on top of this VLM foundation. That lets it learn and explore on its own, which offline data can't provide.
This feels like a pivotal moment. The shift from agents mastering these closed, specialized systems to delivering reliable, real-time control in complex, commercial open worlds. Lumen is an active system that can just survive in these human environments.
It really is. It changes the question from, can an agent play, to how well can this foundation generalize to anything we throw at it?
So here's the thought to leave everyone with. Given that this VLM-based approach can master an action RPG and even intelligently fumble its way through a turn-based strategy game, how quickly might this kind of foundation, once you pair it with continuous online learning, achieve expert-level scale across entirely new genres of high-fidelity, interactive digital worlds? That feels like the real question hanging over both gaming and AI right now.